Let's talk about average velocity and instantaneous velocity. So these two terms both apply to any situation where your function, either f of x or f of t, some function, represents the position of something over time. So really the tip-off tends to be that it's measuring some sort of distance. So like inches, feet, miles, meters, etc. All right, so if your function represents position, we have the following two definitions. So the average velocity from x equals a to x equals b is just the slope between their 2 points. And then the instantaneous velocity at x equals a is the limit as x approaches a of what appears to also be a slope formula. One really important difference I want to point out between these two definitions before we do the example you can see below is that average velocity goes from A to B. So in a problem that's asking for average velocity, it's going to give you essentially like a time interval, right? So two different x values, or if it's measured in t, it'll say two different t values, and you compute your slope. Instantaneous velocity is only at one quick moment in time. So you're only going to have one time value or x value to worry about. Otherwise, they both have a slope formula in them. This instantaneous velocity is really just one of these slope formulas where the BF of B point is just getting increasingly close to or like limiting up to the original point. So it's almost trying to compute the slope at just this one specific point because you're inching closer and closer to it with your other one. Okay, so let's actually see these in action in the example below. So here we have our function. I'm using f of x, but if the variable in here switches to t, just everything in here switches to t as well. All right, so we have this function and we're told it represents the distance in inches of a moving particle from some sort of home, x seconds after being set in motion. Okay, so this does give us units right away. So f is measured in inches, its outputs, and the input x's are measured in seconds. Okay, so there's going to be two questions we answer here. One's average velocity and one is instantaneous velocity. The first part says compute the average velocity of this particle between 0 seconds and 3 seconds. Okay, so we're going to look back up at our definition. This is average velocity between two different time values. So I want to use this formula here, compute the slope between their 2 points. Right now, all I have is the x's. So before I can do the slope, I need to get the y value that goes with each. So I need to compute f of 0 and f of 3 before I can do anything else. So I just want to plug 0 into this formula here. 10 minus 0 minus 3 squared. That'll be 10 minus negative 3 squared is positive 9. So I get 1. And then over here for f of 3, I want to plug 3 into the same formula. 10 minus 3 squared, which is 10 minus 0 is 10. Okay, so I have the point 0, 1 and the point 3, 10. And I want to just compute the slope between those 2 points, and then I'm going to end it by just putting units on my answer. So our average velocity will equal f of 3 minus f of 0 over 3 minus 0. That is 10 minus 1 over 3 minus 0. 9 over 3 is 3. Okay, so my answer number here is 3. Because this was an application problem that has units on everything given, we should also answer in units. So for any velocity, whether it's average velocity or instantaneous velocity, it's going to be your output units, the distance, per input unit, which is seconds in this case. So the time, so distance per time, in this case, it'll be inches per second. So 3 inches per second is my final answer. Okay, and we'll compare this to the second question. So same function, same setup, but now we're asked to compute the instantaneous velocity at x equals 4. So here we had average velocity between two inputs. Here it's instantaneous velocity at one specific moment in time. So we're going to go back up to the definition, and we're using the second definition now. So I'm just going to write this down with a 4 filled in for the A, and then we'll assess what we're working with. So my instantaneous velocity will be the limit as x approaches. I'm using this x value, so 4, f of x minus f of 4 over x minus 4. So just the limit of these average slopes as the second point is getting super, super close to the point f4. Okay, so the denominator here is just x minus 4. It's already ready to go. My job in the next step is to fill in the f of x and the f of 4 in the numerator using this function. So x minus 4 is down there. F of x, I'm just going to go pull the original function formula here. F of x is 10 minus x minus 3 squared, so that's what I'll put in. And then I want to subtract f of 4, which is the y value I get when I plug in 4. So I'm going to do some scratch work on this side to compute it. Just plugging 4 into the original function like we did in the first part of the question. So I get 10 minus 4 minus 3 squared, which is 10 minus 1 is 9. So over here, for the minus f of 4, I'm going to write minus 9. All right, so there's one step we could do maybe right away. In the numerator, we could say, oh, well, 10 minus 9 is 1. But there's not anything else really obvious to do right away. So I could say 1 minus x minus 3 squared, or you could write it as negative x minus 3 squared plus 1. Okay, so now I just have a kind of weird looking limit to compute. So I switch into my limit mode and I say, all right, well, x is approaching a number. Let me try to just plug this number in, see if I could compute a y value with continuity. And unfortunately, when we do that, we get 1 minus 1 on top, which is 0, over another 0 on the bottom. So that 0 over 0 tells me there's likely a hole in the graph of whatever this is at 4. So the limit exists, I just have to kind of do some stuff to figure it out. All right, so we have our 3 tactics. We have factor and cancel, LCD, and conjugate trick. And this numerator here, this really is a polynomial. It's just kind of in a weird format. So this is going to fall into that first category of factor and cancel, but with some extra work at the beginning, just to multiply this out and make it look like a normal function, like a polynomial, before I can actually factor it, because in its current form, it's not factored. It's just weird. Okay, so I'm going to multiply out x minus 3 squared. Continue my work over here. Keeping my limit notation the whole time. So I have 1 minus the expansion of x minus 3 squared, which is x squared minus 6x plus 9. All right, and then I'll distribute this subtraction into the parentheses. 1 minus x squared plus 6x minus 9. And then one more step to at least get this to a normal looking polynomial. I can combine the 1 and the negative 9 to a negative 8. Again, I'm almost out of space, so I'll keep going over here. Continue my limit notation in every step. And again, we could maybe try again to plug in 4. We still get 0 over 0 because we haven't really canceled anything yet. But now at least the numerator looks like a factorable quadratic. Because there's a minus sign outside the x squared, we have some options. We could do factor by grouping, using this as a negative 1, or what I'm going to do, which is just factor out negative 1 first, so that I can do just regular factoring up there. So factor out the negative 1, I get inside x squared minus 6x plus 8. I'm just switching everybody's signs. And then inside the parentheses, this factors nicely into x minus 4x minus 2. And now I can finally see those x minus 4s top and bottom. This is what was creating my 0 over 0. So I can take them out. And now I have a function, negative 1x minus 2, that I can just plug 4 into. So I plug in 4 for the x. This is the moment where the limit notation drops out, of course, because I'm actually plugging in. And I get -2 as my answer. And just like before, I'm going to put units on this. Inches per second, just like up here for the same reason, output units per input unit. And that's my answer to the instantaneous velocity question.